Alright, this is my 16 channel DsPIC based logic analyzer and a little circuit composed of an 8-bit counter and 2 D flip-flops to show an example. It's a little block diagram. There's a 10 megahertz oscillator driving the counter. It's got an input that gets preloaded whenever the terminal counts hit. And then I got a couple flip-flops set up to divide by 2 and then divide by 4. So I was going to light up this example here real quick. So the first time you start the logic analyzer code, it'll assume the logic analyzer is hooked up to COM port 1. That's usually not the case. So if you start up Device Manager, you can find out where it's really living. If you look here closely, the first one listed with the Silicon Labs CP210X USB to UART bridge is COM3. So if we just change this to COM3, we can get access to the logic analyzer. And once it's able to load the logic analyzer and communicate with it, it'll save that info in the registry, so the next time you start it, you don't have to set that again. Get this to fill the screen just right. By default, it comes up in 16 channel mode with 30 nanoseconds per sample mode, and there's a programmable trigger that you can define to say what you want the various signals to be, what state you want them to be in. Do you want rising edge, falling edge? But by default, they say it's level sensitive, and I don't care what the values are, so that makes it easy to see what the lines are doing. So if you just hit ARM/start, it'll grab some samples and display them. And by default is set up to continuously trigger, so once it updates the display, it will wait for a new trigger and update the display again. One thing you can notice is that the display is dancing all over the place and the update rate's kind of slow. So I'll adjust the dancing with making a proper trigger, and the update rate, I'll show how to make that go faster as well. If you hit stop, you can stop the display from updating, and then you can zoom in and scroll around and look closer at the signals. I meant to hit stop. There are markers. If you hold down the left mouse button and move the mouse, or the right mouse button and move the mouse, you can set markers and figure out timing. If I zoom out a bit, you can get the period of the divide by 4. It's 60 microseconds. So I'm doing some fun games with the count to make an interesting wave. To get the screen to update quicker, even if I zoom in, you can still see it's taking about a half second to upload. I have some status LEDs saying when it's waiting for the trigger, when the samples are being acquired by the device, and when the samples are being uploaded. I added a window mode. If you click on that, it makes things go a lot quicker if you're zoomed in. Because instead of updating all the samples to the PC, it only updates what the window is seeing. So as you zoom in, things can get much faster, which is nice. And when you zoom out, it slows down a little bit more. But when you do hit the stop button, it updates all the samples, so when you zoom out, you're able to still see the whole display, so you can still see everything you captured, which is pretty nice. As you can see, by default, the labels are just bit 0 through bit 15, which are not very exciting. So you can click on the labels and change the names to what the signals really are. And I've done that already and saved it in a configuration file. So if I load that configuration file back up, the names have changed to what they are. And you can resample again, stop. And you can see that the red line is the 10 megahertz oscillator, and then followed by the 8 bits of the counter. And the blue line here is the terminal count, which is set to 0 when the count goes to 0. The purple line is divide by 2, the first flip-flop. The yellow line is divide by 4, the second flop. And I played some games with the preload value to the counter. I made the preload a function of the div2 output. So that allowed me to make the div2 a non-50% duty cycle square wave. If I zoom out a bit, you can see that a little more clearer. And then the yellow wave is showing that even if the input's not 50% duty cycle, you get something pretty good looking. This define trigger button allows you to set the trigger. It uses the labels. So the trigger I set up here is to say when the terminal count is 0, which is when you're at 0, and the divide 2 is a 1, and the divide 4 is a 0. And you can change the edge to either rising, falling, or level. And then there's a button to say continuous trigger or just do a single shot. So once you do that, then you can get a much more stable screen. Zoom over to the left, zoom in to see what's going on here. But so that's basically what's going on here. You can, and I'll zoom in a little farther to show you that at 10 megahertz, that's 50 megahertz, 50 nanoseconds for the clock high and 50 nanoseconds for the clock low. Since we're sampling at 30 nanoseconds, it doesn't look like a pure square wave, even though it pretty much is. I've seen it on other equipment that it does make a nice 50% duty cycle, but reality starts raising its head where the sampling rate at 30 nanoseconds, you're either getting one cycle at 30 nanoseconds, which is shown here, so you'll say 0.03 microseconds, and that's followed by another cycle of 60 nanoseconds. So if you go rising edge to rising edge, it'll say 90 nanoseconds or 0.09 microseconds. But if you average that out, it's going to be 100 microseconds. One thing is the sampling rate, there's a list of different sampling rates you can use. You can go from 30 nanoseconds all the way up to 250 microseconds. And I always try to tell people to start with the fastest sampling rate, see how much data you can get, and then slow it down if you're not getting enough of your samples. And I can show, I'll zoom out a bit and show what happens if you pick the wrong number. So this is still at 30 nanoseconds, but if I zoom out and run 150 nanoseconds, you can see that the clock starts vanishing occasionally. If I zoom out more, of course now it's not going to show that, but you can see it there. If I can stop it, get one. If we zoom in on the clock, you can see it'll start lying and see it's saying that the clock cycle is 300 nanoseconds, and we already know it's more like 100 nanoseconds. So this is called aliasing problems, where if you sample too slow, the data starts getting very goofy looking. And I'll make that even more apparent if we go out to 5 microseconds. You can see the clock actually looks like it's vanishing or slowing down. And this is what happens when you sample too slow. Our buddy Shannon came up with some great theories and math to describe what happens if you sample too slow a fast running signal. But as you can see, the divide by 4 output still looks okay because it's a 60 microsecond period on that one, and sampling at 5 microseconds is plenty fast enough to still get the square wave out of it. But you can see the low order bits of the counter are getting all wonky looking, same as a 10 megahertz clock. Last thing I wanted to show is what happens when you sample very slowly. Change it to turn off continuous mode. But when you hit ARM, the screen changes, says the trigger's been found, but it says it's going to take it's counting down from 6 seconds for how long it takes to get the sample. There's 24,000 samples, and if you're at 250 microseconds per sample, it takes 1 second to get every 4,000 samples, so it takes 6 seconds to fill up memory. As you start shrinking the number of channels down, that number can get pretty high. Like if we go down to 4 channels and just go with 50 microseconds, showing it's taking 4 seconds. If I go up to 250, it's taking 24 seconds. And I also put a little display on that acquire samples thing. It's showing it's currently grabbing the samples. There's another 17 seconds to go. If you get bored, you can hit the cancel button and that'll just stop it. But if you ever hit cancel, when you're in window mode, it will not fetch the remaining samples of the outside the window you're looking at. Sometimes it's able to do that, and other times it's not. Depends where it's at while it's acquiring samples, whether you'll get all your samples or not. So if you can be patient, use the stop button over the cancel. Go back and get our original configuration. So back at 30 nanoseconds per sample, 16 channels, and everything's happy again. So that's basically it. You can also save samples to a file and load them back up. And the file is just a basic ASCII file, so you can actually do some post-processing if you want to write some Python or Perl code or C++ code or whatever to do some math on the samples if you want. And the other thing I wanted to talk about is I have the pull-up and pull-down resistors in the processor, so you can leave it's how you deal with the floating inputs, whether they're going to be yanked to the ground or yanked to 3.3 volts. But that's basically it. You can read the firmware version, which is 17.04 right now, and you can read the number of samples. These are kind of like things I do for sanity checks. The last feature here is you can download firmware and verify firmware. So if I produce or someone else produces new code for the PIC, the DsPIC, you can download the firmware without getting out a microchip programmer. You can just do it in circuit, and away you'll be able to go again. So that's it.